Hello, everyone. Welcome back to the last day of the conference. It's good to see still there are many people willing to wake up that early just to catch up with our latest crazy, exciting research. So today, the schedule will be we'll have two keynotes and then followed by a lunch break. Apologies, it's so short, but we just don't want to have people missing the award ceremony, and also we don't want people to miss their flights. So we have a relatively short lunch breaks. After that, we will have a tutorial and by the last oral session. And we will have our award ceremony, which is exciting. So if you think you have a chance to win the best paper award or run up, do stay. Otherwise, you will miss your big moments in your life, which is such a pity. So you don't want to do that. Now, keep awake, everyone. Now let's start our excitement today. So the first excitement today is a keynote speech given by Michael Galtin from Google, who will talk about graph foundation models at Google. Michael Galtin is a senior research scientist in Google Research, specializing in graph learning and reasoning. Before joining Google, he was an AI research scientist at the Intel Labs in San Diego and a postdoctoral fellow at Mila and McGill University. Now let's welcome Mike on the stage to give the big excitement today.
Thank you. Yeah, thank you very much for getting up this early. Keynotes at 9 a.m. The funniest keynote. Yeah, so today I'd like to talk about graph learning in 2026. So what would be the interesting avenues to work in the area? It's a bit opinionated thing. Can I? Oh yeah, perfect. Thank you. So a few necessary words about our organization at Google. So we are running large-scale graph mining optimization algorithms. We are supporting pretty much every product at Google which has a lot of graphs. Actually, the largest graphs in the industry so far, and these have to be billion, even more. Mm-hmm. Already, yeah. So we're dealing with the pretty large graphs on the order of billion, sometimes even more, even larger graphs. And we do a lot of engineering, production engineering, and research as well. So yeah, pretty much every product like Maps, YouTube, ads, and so on, they are powered by graphs, and we help product groups deploy those and keep evolving them further. So specifically the GNN team, we're focusing on research and with big publications, expo talks, and so on here and there. We also do some open source development, and there will be, I think we'll be ready to talk more about it in the next few months. But we also do a lot of infra work and modeling to support custom applications. So it's pretty much the full stack from research to production. Alrighty, so after the necessary introduction, perhaps the main topic I've been hearing among graph learning researchers recently this year and a few months is that yeah, like everybody's doing Gen AI now. Those happy Gen AI people, they're taking most of the community focus, but then yeah, other fields feel a little bit neglected. So have you ever felt this? Some equivariance already starts looking like a little bit like shaky, and you say like not necessarily baking in some physical equivariances, but just slap some latent model and it works better. But GNNs, yeah, feel completely like neglected at this point. Vanilla GNN research, I would say. So everybody's doing some more important applications. People are switching to other fields. So my job for today for you is to convince you that, well, like actually it's not that bad with GNN research so far, with graph learning in general. There is plenty of interesting applications. Yeah, so what follows is a highly opinionated list of topics which we believe would be interesting to work in graph learning in the next year. So first, starting that in 2025, looking back, we have just 2 weeks, so we can say that the graphs are in work everywhere, starting from relational databases, going to LLM reasoning, graphs very much. encoding graphs, some generative models in AI for science, agentic systems, hardware design, combinatorial optimization. Specifically, I'll be talking about those three as probably the most exciting, the most open things to talk about. Agentic systems, hardware design, and databases, those were specifically one of the coolest areas where graph learning can be applied off the shelf. So first, starting with the graph foundation models that we've been investing at Google in them quite substantially, and they're already in production. So the traditional graph learning research has been done in a way that you have some data set, you have a tailored model for that, and then it solves a certain task. So whatever GNN architecture is proposed in the paper, it's trained separately on each specific data set, and then people build nice tables and claim state of the art. So, well, it's kind of old, so don't do this anymore in 2026. This is a bad practice. And even worse is evaluating that on those super old data sets, like Core Sciencey or PubMed, OGBN archive. So this is like a standard suite of bad data sets, which should not appear in papers anymore, we believe, because there are so many more interesting tasks. What instead you should do is to switch to some foundational setup, meaning that evaluating GNNs in setups which probe for generalization and for transfer, meaning that now instead of training all those separate models, we can train the same backbone and generalize to different applications in different tasks, from node level to link level to graph level. And it's certainly possible, because what's the most important part here is that to learn transferable representations. So that, I'll talk about some critique of some existing works. So learning a representation is important, and if you have that, you can transfer to unseen graphs and tasks. Specifically for representation learning, what is interesting to look at, and so far there hasn't been that many papers whatsoever, is generalization to unseen graphs and tasks. How can we train model on small graphs or even synthetic graphs and generalize to some real-world applications? What's the structure of the latent space? How does my latent space look like? Is there any specific details we can extract, say, for node level, for link level problems? And is there any scaling so far? So far, there has actually been problematic to see some scaling patterns. And open challenges. Some examples for those open challenges. For instance, heterogeneous features. The simple example we have one graph with 10 numerical features, graph B has 5 categorical features. Originally, you would train different models because you need different projection layer before going to, say, into GNN processing. And that's the first challenge. Like, what would be the universal latent space for them? How can you actually turn 10 numerical features in the same latent space as 5 categorical features? Some of those approaches were considered yesterday at the GFM tutorial, so that was actually a pretty nice overview of what people are doing right now. But there is more to that. There are sparse and dense features. There are graphs without features at all. There are graphs with some, say, graph level features. And well, there is a variety of those different featurization strategies, and they have to be transported in the same latent space. The same, well, the other one is how can we generalize to different problems? So one model should generalize to classifying over 10 labels and 100 labels. And this is also non-trivial, because originally you would slap some, say, MLP decoder for the target number of classes. And now we can say, well, can I have 2 different MLPs, but then I cannot train the MLP on 100 classes if my training data only has 10. So this is also was originally, well, quite some non-trivial application, non-trivial problem. How can we generalize to different number of classes? Now it's almost a solved problem. But say if we look how to generalize between node level and link level problems, how can we train a model on node classification, generalize to link prediction? That is still very much a problem, because those tasks need different symmetries. Alrighty, and recently we have seen quite some extended community focus on GFMs, and we like that very much. So not just looking at citations, but people do extend those papers. So we're pretty happy to see that. But there are also plenty of events like tutorials at log, a few events that were at the graph learning workshop at NeurIPS, and some of the work we published. So that's actually a nice point to measure the community involvement into the topic, and so far it's been pretty exciting. So generally the interest is growing. And specifically what we have done recently is some work on GFMs for relational data, and we recently put out a nice blog post about that. So the idea there is that we turn relational databases as heterogeneous graphs. The rules of transformation are pretty straightforward, where each row becomes a node, foreign keys become edges. Each table becomes a node type, and we treat everything else in the columns as node features. And there are some so no gifs here, I believe. Yeah, there was a GIF. So sorry, no animation today. The idea is that we can pre-train on one set of graphs and run inference on everything else. And we've been running this model in ads, in some spam detection problems. And so far it's been showing dramatic improvements over tabular models. So just adding graph connectivity to those problems results in enormous gains. But in some problem we get up to 2x performance improvement, in some other problem even larger, with larger graphs, we get almost like 10x better performance. And it's just adding some graph information to the classifier. So that's that was the first example how when we see like, wow, that's actually really cool to see. And the response from our partners in production was very warm. Like they want to see more. They would like to work more and get new versions of those new toys as fast as possible. So some lessons learned from that is that, well, learning representation is important. That having one model to learn all the node graph level tasks, that's certainly possible. Perhaps the third point I would specifically focus on, which is the absolute information doesn't transfer, but relative encoding does. So it actually doesn't matter which features you have. It's most important is how nodes interact with those features, and what's the relative interaction between them. So that is more important than focusing on what is the absolute feature value, like 0.5 or 0.99. What's important is to scale the diversity. So some synthetic data is certainly useful, but it only works to a certain extent. So probably mixing some real and synthetic data might be a good idea. And there is also a significant portion of engineering here. So there is quite some extended infra to train and run those things in production. And we invested quite a lot of time in engineering. So some part of the talk was supposed to be about some upcoming graph processing library, but we aren't ready yet to talk about that. So we'll be hopefully in the position to talk more about it in the next few months. But generally, training and inference efficiency, this is an important component of running those things at Google scale. Alrighty, so the second topic, which we believe is quite interesting and important, it will be graphs and agents. And we've seen some tremendous success with benchmarking when LLMs and frontier models are allowed to use agents and tools. We've seen that in coding, and some big examples, some Swebench, Verify, Swebench Pro, some other big data sets that are reported in big new model releases. Like there was one yesterday, you might have seen. The computer use, that's how models can actually move the mouse and click on a browser and perform some computer use tasks. Maths and science, I think that's the most important right now for, say, ML researchers who want to compete with the Humanity Last exam in ARC, AGI, and so forth. But say Amy is already considered a solved problem. So the frontier is moving very fast. And generally, question answering, retrieval, I think non-agentic approaches there are now almost, well, non-existent. Yeah, so actually if we look what is understood under the multi-agent system so far is very much like LLM with tools, or maybe few LLMs. So it's a star-shaped pattern when you have some orchestrated LLM which receives a task, it sends a bunch of queries to tools, and maybe sends a few queries to smaller LLMs, and then it aggregates the responses and sends the answer. And this is like the standard pattern of multi-agent systems. You can slap some MCP servers, and then you can claim, wow, we got a multi-agent system. What we believe is actually more interesting and far more performant in the longer term is to have graphs of LLMs. So where each node is an LLM, and they can talk to each other. So not just one orchestrator node receives the task, but all of them get some portion of a task, and they talk to each other to try to derive the best possible pattern of solving. So it's saving among many axes, from token budget to just pure money. Well, a few examples actually how it works is that we showed them in the recent publication called AgentStat. So this is a work on both coordination and collaborative reasoning. And we study there how those communication graphs, how graph topology between different agents affects the ability to solve the task. And here we are looking at some classical algorithms from distributed computing literature, starting from, say, graph matching to consensus to leader election. But now every node is a LLM with API, so it can be queried, and they are aware of their neighbors. So that's the most important part. So they're not allowed to talk to all of the other nodes. They're only allowed to talk to their immediate neighbors. And some of those tasks require several hops of message passing, but now it's message passing literally in natural language. Yeah, so some example how it works, say on a chain. This is one of the simplest forms of a graph. So only the middle node can talk to both neighbors, and those two on the left and right, they can only talk to their immediate neighbor, and they exchange messages and are able to solve, say, the simplest consensus problem here. So practically, if we measure the performance, say, on the right-hand side, those results were from May 2025. So we'll already have a newer generational models, which will be interesting to evaluate. We are on it as well. But generally, we see that the current Pareto frontier is already pretty promising. We'll be moving it. We will expect that new generational models will be moving it into the upper left corner. So it will be even cheaper, and we'll have even better performance. So far, we see that reasoning models, thinking models, generally perform much better. They are aware of the graph environment, of the topology that they exist on the graph, and they have to talk to each other to derive some basic knowledge about the network. And then on the left-hand side is an interesting experiment. We set out trying to scale it up as much as we can. So the most of the existing literature in multi-agent systems, they work with on a scale of like 5, maybe 10 agents, and we scale it up to 100. And actually, there is nothing specifically hard in scaling up to 1,000. It's only a question of infrastructure, and we can generate infinitely sized problems with that. And we see that as soon as you go, say, to already 20 agents, the performance drops significantly. Only on the consensus task, which is the easiest actually from the entire suite, we see that sometimes it can get non-trivial performance even up to, say, 80 or 90 agents. But for other problems, it quickly drops to 0. So there is actually plenty of opportunities to understand what's going on there and improve those numbers. So ideally, we would like all those blocks to be 100%, pretty much like all those pictures you see in the needle in a haystack benchmarks. But so far, it's been a lot of problems, and on the website, you can see the fail cases. What's happening? Why in many problems the numbers are so low? So we do publish a lot of results, including those topologies. So this is the example of a network of 16 agents, and on each edge, we can see the history of the communications between those agents and how they communicate and try to derive a strategy of problem solving. So yeah, going back here, so if we are increasing the size of a network to 20, 30, and so on, a lot of problems very quickly, their performance very quickly drops to zero, and this is also due to context compression, context inefficiency, some I wouldn't say post-training issues that some models like flat out refuse to talk to each other and they give up very quickly and say, okay, well, I have like 15 neighbors. That's too much. That's too much, man. I'll just don't want to talk to you guys anymore. Or some others, some of the nodes can be actually actively adversary, and they start flooding the network with some wrong information. And we want to design networks which will be robust to those bad actors. So there is a plenty of opportunities to build things on top of it, from basic context compression, multi-agent system interaction to robustness and safety, and it opens a lot of doors here. So that's why we see it's a pretty cool topic to work for 2026 already. And then perhaps the third and the largest part of the talk is finally a new frontier of new graph learning applications. And here we are very happy to announce that we finally released the Graph Bench. So some time ago at ICML, we published an opinion piece, very opinionated people, that the graph learning as a field need new tasks to maintain its relevance in comparison with Gen AI that you see, like the scope of tasks that Gen AI is solving versus the scope of tasks that previously GNS were solving, they were pretty much incomparable. And it was a regular source of frustration for researchers, saying like, well, why do we actually need to work with citation graphs and this core SIT or OGB problems if we can solve like protein folding or some other, or cell driving or some other practically important tasks? So, well, the first natural thing, we actually acknowledge the problem, and we see quite some resonance, I would say, with the community, with this paper that, yeah, actually, we started hearing with the researchers that, yeah, that's actually true. Do you have those new tasks in mind? So we stated the problem that we need new problems, and do you have those problems? And well, the answer is yes. That finally out just 2 days ago in arXiv, we are very happy to announce the Graph Bench, which is the next generation of graph learning benchmarking. So this is a massive, massive collaboration led by Christopher's lab in Aachen. And we're very grateful to have the opportunity to collaborate on that. So yeah, 20 people, all the arXiv submission and the website is already there. So let's actually dive into it. What's there? So what I find specifically interesting is that we're going much further from social networks and citation benchmarks here. We are introducing a lot more new domains and data sets. We still do have separation on node level graph, node edge level, graph level tasks. We also introduced a new benchmark for generation. And I'll be going through all those tasks one by one. But generally, the Graph Bench framework itself provides not just standard splits, but also evaluation protocols, benchmarks. So all the standard suite of tools that you need to quickly evaluate your model. So perhaps something that is close to my heart, I find it interesting a lot in what specific calls in the industry too. Those are chip design tasks. And we frame it as a generative modeling. So the problem is going from the Boolean function to a graph, which actually not just a graph, but it will be an inverted graph. And our baselines here are strong solvers, which like a pretty much industry standard, which do not use any neural nets so far. And the problem here too is to optimize those AIG graphs. So we are given some logical formula, say out of 3 variables, and we want to implement it with the smallest number of gates. Something that is implemented in silicon, so like with transistors and some with some physical units that consume space on a canvas. So the problem is simple. The smaller the graph is, the better. So we spend fewer gates, we spend fewer resources to bake the chip while maintaining the same logical consistency. And it's been, well, actually, it's NP-hard problem, the first thing to do. And there's been a lot of heuristic-based solvers with that, and so far neural nets pretty much underperforming in this. And specifically with this data set we collected, which it has about 1 million graphs. So all of them have some not optimal, but close to optimal solutions, which we were computing using those strong baselines. And those graphs can be pretty large, up to 300 nodes. And generally, we want to target more and more complex circuits over there. So yeah, with 3 nodes, the graphs are pretty easy, but if you scale it up to say even 8 inputs, it becomes this mess. So yeah, it's very hard to make sense of this with a human eye. And that's why solvers time or runtime grows very, very badly depending on the size of a problem. And I would say for industry grade problems that would be on the scale of say 64 on 128 inputs. Say if you think about modern matrix multiplication units, depending on the size, yeah, they can go for 128 to 256. So 8 units is computationally already pretty hard, but going to modern parts, modern circuits would be even harder. And we'll be gradually adding the complexity to this benchmark. So 1 million data points is already enough to train some interesting generative model. And so far, actually for specifically 2D generative models, there wasn't any good benchmark so far. People were evaluating on some ER graphs, on SBM graphs, sometimes on molecules, but for molecules doesn't make a lot of sense. So finally, there is some sensical task for doing 2D graph generation. So yeah, we're very happy to see the community coming up with some solutions that can beat the benchmark. So far, it's actually pretty hard for neural nets to beat even classical solvers. So that will be a very exciting time. The next one is electronic circuits. So those are already analog circuits, and we want to estimate certain electrical parameters. So in the basic case, for instance, the voltage conversion radio, which we want to compute on the circuit level. So it's the graph level task. We have graphs of very different sizes of different number of inputs. Sometimes you can treat them actually even as hypergraphs as well. So modeling wise, it's pretty flexible. Sure, there is a new version of social networks, actually finally something better than Courtside Theorem PubMed. It's actually coming from Bluesky. And it's a dump of real social network state. We have several splits of several different sizes, like AK medium size, like about 10 million edges, and a few 100,000 nodes. And we want to predict certain interactions between users on the server. Something specifically interesting for combinatorial optimization community is the SAT solving problems, and they come from practically relevant tasks that have to do, for instance, with the verification of digital circuits, verification of software, with cryptography too. So those things are used in real-world applications. So moving the needle there is very important, can bring actual practical benefits and a lot of monetary impact. And for combinatorial optimization, similarly, there hasn't been any good big data set so far, and we have roughly 300,000 graphs of very different sizes again. And we're targeting so far just a relatively basic set of problems about maximum independence set, max cut, and graph coloring on very different families of graphs. Still, we are in an NP-hard regime. The data set is pretty large, so we can build transferable model. So actually, the focus of that, of those models, is that we want, in cases for SAT solving, in the case for combinatorial optimization, we are not just interested in solving the best one of the specific problems. What we are interested in is creating a model that can solve those tasks with one set of weights. So you would train a model that can solve those different combinatorial optimization tasks, or a model that can solve different SAT instances, and not train every model for each of those new problems. But we want to be more generalist and transferable. So still reminding those big trail of foundation models. Yeah, and a few more tasks will be algorithmic reasoning. So here we're building upon CLRS benchmark. Now we are scaling up the inference data set up to 2000 nodes after training on 16. So that's a nice size generalization setup. And we're targeting here a bunch of pretty complex graph algorithms. Again, the data set is pretty large, so you can train some beefy nets here. And the last but not least is weather forecasting. So it's been pretty big progress in the area so far. DeepMind released GraphCast. It's our baseline here. So here you can compete with one of the latest DeepMind's model. GraphCast was published, I think, last year at Nature. There are some other versions of it which work on different resolution levels, but practically the problem is that the Earth's surface is split in a mesh with some 64 by 32 grid, and our task is to evaluate certain weather characteristics in the nodes of this grid, and it's split into almost 100,000 graphs with different numbers of with differently sized graphs. The data set itself is pretty large too, so it's a perfect example of trying to come up with the baselines that would beat certain big industrial baselines. And so far, actually, the baselines underperform those industrial works like GraphCast. So there is still plenty of room to improve the performance there. With that, I'll say, well, everything is already open source. You can already pip install the library. Check out the website that has much detailed description of those tasks, about the splits, about the data, how we can install and evaluate, attach it to the framework of your choice. And with that, I think, yeah, I'm ready to take some questions. Thank you.
Thank you for a great talk. Any questions from in-person audience? For online attendees, you can ask on Slack. I can also check. Okay. So one online attendee have a question, if this is not a problem. Okay. So their question would be, if the focus of NP-hard solvable problems can produce that the change on the performance of each agent that is not fast or accurate enough to be solved with this approach, similar to the automaton NP-hard problem.
I wonder if it relates to the agents part of the graph bench part. Is there any detail? Or the person is asking if we can combine some SAT solvers, or well, the approaches to solve NP-hard problems for this optimization of networks on the agents net. Well, the answer is generally yes. That would be possible. Although it seems that right now this is not the most important problem. The most important problem is to keep all the agents, LLMs, coherent with respect to the input, but with the task, and to guide them as like a group of kids towards towards one problem, so they will not spread out during the execution time.
Thank you. So they confirm online that yes, and both they are interested. Any question from in person? Yeah.
Thank you. Great talk. The question is about the relational foundation model that you mentioned at the beginning. So because these kind of graphs are based on the, for example, daily transactional database can be, for example, customers, orders, this kind of transactions, and they're updating the continuously. Do you think how frequent these foundation models need retraining?
Well, that's the whole point. They don't have to be retrained. That's the idea that we don't need to retrain them that often.
Yes.
How not often? I would say, well, heavily depends on the quality, but we don't want to retrain it every week or every month. So we want the same model to work on a pretty long time horizon. and it would still, well, it shows that it still works pretty well, even being trained on much older data. Then you can, yeah, if you want, you can update it, add more data, and can continuously train it. But so far, the whole premise of those transferable models is that you don't have to retrain them every day or every week when the data updates.
So you're saying that the few shot or zero shot features of these models can be robust against the.
Yes. Yeah, precisely.
Interesting. Thank you.
Thank you.
Yeah, thanks for the nice talk. So my question is about the agents network and like what's the motivation for using a network to organize the communication between agents? Like we humans have networks because we have limited cognition, like to transmit knowledge, but these agents have infinite capacity to process. They can transfer all the weights that they have. So basically, right, it would be like a Neuralink kind of approach. So I'm thinking like whether you saw that if there is real motivation to have like a sparse communication structure between agents compared to humans that have again cognition capacities that we know
Yeah,
are limited.
yes. So there are at least two big motivations. The first one is the cost. So the right-hand side of this chart. So right now, a lot of those multi-agent systems are homogeneous, meaning that you just use whatever the most powerful or the same LLM as a backbone for all your agents, and sometimes it gets way too expensive, and you won't get any extra performance spending so much money. So it's natural to have more heterogeneous setups when certain nodes which don't require to aggregate a lot of information or solve very hard tasks, those have to be less capable models and will still be perfectly fine. So you'll save a lot of money in terms of API costs, in terms of tokens, in terms of inference time, and so on. And so far, that hasn't been explored very much. The second problem is, well, they go out of context pretty fast. So if you work, say, with coding applications or something that requires you building and understanding large code bases, they very quickly go out of context window. And you want to divide and conquer there, so you want to separate the work between different parts and orchestrate with each other. So some worker will be writing tasks, another one will be building some deployment infra, and so on. So you want to parallelize the work and bypass this context limitation. Even if you have very large models like Gemini with like 10 million tokens of context, still with very large repositories, yeah, they'll need much more.
Thank you.
Any other questions from in person?
Hi, thanks for the great talk. So one thing that wasn't clear to me was with all the benchmark construction and foundation models, it wasn't clear to me whether you guys are working on sort of commercializing a pre-trained model for commercial use. So can you talk a little bit about that?
Or you mean for GraphBench, this one?
Yeah. So the your model node there, like, is that something that will be sort of available after pre-training for commercial use?
Well, it depends on the author. So we are providing the benchmark. We'll probably release a few baselines, yes. It's certainly possible for the community to come up with models of different restrictions, of different usages. Perhaps what is important, what we would like to focus on here is that solving those tasks is practically important. So moving the needle in any of those problems directly translates to monetary impact in dollars. Like, very differently from citation networks. So if the community comes up with some of those models, that transferable models that can generalize across those different tasks, that will be a very good achievement. We'll be happy to see that. And well, whether they will be closed source and open sourced, well, there is no requirement in this benchmark specifically. It can be closed source model too. We'll just be happy to see if any performance improvement on those tasks.
Thank you. Any other questions from in-person audience? Or I will pick online questions. All right, so if we want to train a graph of LLMs, what will be the potential tasks?
Can you repeat, please?
So if if we train a graph of LLMs or agents, what will be the task to consider?
If we change the graph.
So if we train a model on a graph of
Ah.
LLMs, what will be the task of that?
Oh, if we train a model. Oh, I see. Okay, so the question is, if what happens if what kind of problems we are able to solve if we are actually training the model to operate on this right-hand side setup with when they're working together on a certain network topology? Well, it's actually a wonderful question. So because right now, those generally the state of the art today that they cannot work well in those setups. So they were not trained in multi-agent setups. So usually it will be some sort of additional post-training that you make the model somehow aware of environment and that it's working with somebody else. So very, very few people do that right now. So what you can do if you allow models, if you make the models aware of their environment and that they are actually working together with somebody else, well, perhaps the best thing I can imagine so far, it will be trying to solve the problems in parallel way, so and split the costs. So going again, showing this is the most popular chart I'll be showing so far on the right hand side. So the task would be to move the performance to the upper left corner, so where you can add more agents which will be cheaper and they can be progressively more capable in solving more important tasks. And not just on this benchmark, but also on practical things like coding, like reasoning, like hard computer use tasks, something that requires a lot of back and forth communication with the user or without the user. So, well, there is a plenty of agentic applications from everything we can see here. Those have been using so far some agentic harnesses. So all the multi-agent systems are very amenable in moving the needle in one of those benchmarks.
Yeah, thank you. Yeah, I personally think of kind of follow-up of this. Like, if you have a bunch of LLMs or agents among automatic cars driving, then they can also communicate probably, and this will be kind of useful.
Yeah, that sounds like a wonderful use case.
Yeah. Okay. Any other questions from in person? Oh, I'll ask another online question. Okay. So the question is about the library. So about the graph bench you propose. Does the library allow us to use part of the graphs, or do we have to use the whole of the probably computationally and storage inefficient kind of graph?
It's up to the model. So generally, you can slice it up as much as you want. So a lot of the problems here in, say, all the areas other than social networks, they are relatively small graphs on the order of, say, 100,000 nodes. So usually those graphs you can fit in memory even entirely. When it comes to, say, social networks, when we come to slightly larger, like 10 million edges, a few 100,000 nodes, then it's actually up to the model. So you can do sampling, you can come up with some interesting tricks to try to treat those graphs as full batch processing too. So no big limitation here whatsoever.
Thank you. Any questions? Okay.
So I think this is more like a practical question about this proliferation of graph benchmarks, right? So now every time you submit a paper, they will say like, oh, you didn't run your model on like the largest graph from this benchmark, and it's like graph coloring, like, so it's some hard problem and you have to run on a billion node graph. You know, there are like probably like 10 of those already, so everyone can ask for their own benchmark. And nobody says like, oh, my benchmark's for this kind of problem, that benchmark's for a different problem. So how do we navigate this explosion of number of benchmarks? Which I think in part is caused by the NeurIPS benchmarks track that everyone is creating benchmarks now. Like, so say as reviewers or like researchers, how do we decide which benchmarks make sense for which problems?
Yeah, well, we actually did the entire position paper saying that most of the benchmarks current in literature don't make sense. So there are only very, very few problems which are actually worth being solved. And I can count them in my one hand. So yeah, the community definitely can continue exercising frustration and running a bunch of synthetic benchmarks like Zinc. but they don't make practical sense. And showing some impact on them is kind of fruitless. So if you improve the number on zinc on 0.001, nobody cares about that anymore because it doesn't translate any practical task. So here we actually come up with a suite of very important practical tasks. So we would advocate that running evaluations on those benchmarks is actually more important than anything else before.
So you think that your benchmarks, the ultimate one, nobody's gonna write next year another paper like that. They have a
Oh, it certainly will be more, and actually we're pretty open to see more interesting tasks. Perhaps the most important part is that, well, we would like to see their practical importance. So we would like to see that solving graph coloring problem, as you mentioned, not just for the sake of graph coloring, but actually for some practical application.
no, thank you. Thanks.
Any other questions from in person? Okay, I'll ask one question. So just following up on the size or criticism from reviewers, as researchers working in academia, we don't have that many computing resources. So given those large sizes of benchmarks, how do you think researchers in academia can contribute and not being criticized by not evaluating our models on those huge, tremendous data sets? Like basically how to benchmark or do a fair evaluation on our probably not industrial level models.
Well, the good part is that we can, so far, say in the GNN literature, we do see a correlation between the performance on smaller data sets and larger data sets. That's something that doesn't happen every day, say in modern frontier LLM research. A lot of experiments on smaller models and a lot of results on smaller models does not correspond to performance on larger sizes. Well, here, so far, we are pretty optimistic that if you, say, solve problems on chip design on those relatively small graphs, if you increase the size, it will likely improve as well. And in fact, the majority of the problems here, other than social networks, they are all pretty small graphs. So it's actually friendly for academic budget. Some splits of those data sets are very much, well, you can use them as like proof of concept, MVP splits just to see if, for sanity check if the model is working. So that is, yeah, that's what we had in mind too. So basically the answer is, it's very much amenable for academic computing budgets, and the gains will probably translate to larger sizes, to problems of larger size.
Thank you. Any final questions from in-person audience? Otherwise, I will ask the final question. So, given that you're working in industry, we do have a bunch of exciting models coming up here, but they might not be industrial ready, right, to be implemented. So you have already introduced a bunch of agents and LLM models and graph foundation model kind of thing. What do you think is the current critical gap that we can fill in for them to actually being implemented in the real world?
I would say infrastructure and engineering is still important, and so far it has been quite a neglected part of GNN research. Specifically, I'm talking about say fast kernels and fast optimization, data efficiency that hasn't been in the focus so far. So LLM people already internalized, especially in the post-training setup, that having fast inference corresponds to, say, faster rollout, so you can afford more RL steps. While, because the GNN so far have been trained on toy data sets where the entire iteration on core, it takes like a half a second or even smaller, then there wasn't any significant focus on performance so far. And that's a big gap when you want to productionize those things, because then you actually have to think about the inference time, about engineering aspects, how fast is the GNN, do you need to put more layers so it can go more wider, and so on. So we started working a little bit in that direction a few years ago, because when we worked on Ultra, and we were happy to see some works yesterday from yesterday's workshop, which also took an extra mile and actually implemented some of the most important parts as CUDA kernels, as Triton kernels. So that's, to me, that's pretty amazing. We'd like to see more. We also worked a little on some geometric geometric models and trying to speed up their spherical harmonics with tridimensionals too. So engineering and data is as important as the problem itself. So perhaps, yeah, that the message that LLM world internalized quite some time, and would be nice for the graph learning community to invest their efforts to scalable data pipelines, training, optimization, inference. That's all is as important as model training and getting good numbers. If you need to train a model for like 30 days to get a very marginal improvement on benchmark, that kind of nobody cares about that. You want to have you want to be able to train the model, train the model on larger data, and to be probably scalable in the sense if you're adding more data and add more parameters, it actually works better. And so far, this has been also a problem for some GFM style works too. That adding more parameters, adding more data doesn't necessarily translate into bigger numbers. And that all has to do with the optimization and with efficiency.
Yeah, so we are right about to be 10 a.m. And let's thank our great speaker again for the great discussion and presentation. And also thank you for all your great questions. So we are going to have our second keynote. We may have 2 minutes of short break, and I will hand over to Ali, who is going to be the next chair.
have the pleasure to have Melania Weber from the Harvard University. She's a professor in uh, applied mathematics and computer science, and she's going to talk about the feature geometry guides model design in deep learning. The floor is yours. Thank you.
Thank you. And thanks to the organizers for inviting me to speak. It's great to be here. So my talk today will have two parts. In the first one, we're actually talking about deep learning on graphs, so well in line with the theme of the conference. And then in the second part, we will use graphs as a tool to understand feature geometry in more general architectures. So in the first part of the talk, I don't need to point out to this audience that message passing graph neural networks have been very successful, have been applied in many graph domains. We've heard of about that, of course, in the previous talks. But there are still some challenges that remain in the design and the structure of such models. And one quite critical challenge that arises are instabilities. And in particular, instabilities that arise in deep models. So as you know, if we want to, if we have a downstream task that requires us to capture long-range dependencies in the model well, then we need to build deep graph neural networks in order to be able to encode that information. And deep graph neural networks suffer from instabilities, such as, for instance, oversmoothing. So what oversmoothing means, and we will be a bit more careful later on, but just as a brief preview here, oversmoothing means that after just a few layers, the representations of nodes that initially have dissimilar features become more and more similar. So we have a kind of collapse of representational information, and that can really hurt us in downstream tasks. This kind of instability that's really well studied in graph neural networks also actually arises in other architectures, in particular in other structured models. And there it's sometimes studied as under the name of vanishing and exploding gradients, if you have heard of that. And what I'll be talking about is one remedy, how we can change the design of a message passing graph neural network to provably avoid that this fact arises by redesigning the way we implement graph convolutions. And in the second part of the talk, as promised, we will move on to some more general or non-geometric architectures. And we want to use graphs, in particular geometric graphs, as a way of studying the feature representations that such models learn. And we will use tools from discrete differential geometry, namely discrete Ricci curvature and an associated geometric flow, to understand the evolution of those feature representations and what that can tell us about model design. Okay, so that's the plan for today, but let me go back to the instabilities and how we can design provably stable deep graph neural networks. So the kind of architectures that I'm going to talk about will be exclusively message passing graph neural networks. Of course, there's some other concepts and some other model classes. We heard about some of that in the previous talk. But here we will focus on the message passing paradigm that I'm assuming everybody in this audience is already very familiar with. And then we had already discussed oversmoothing a little bit. Let me just say in a bit more detail how oversmoothing arises. So in the message passing paradigm, or in each message passing layer, we have essentially two key functions, right? We have an aggregation function that computes the message over the one-hop neighborhood of each graph. And that aggregation function we can essentially think of as a kind of statistical aggregation, an average or some other statistical aggregator. And then the update function, of course, is some learnable parameterized function. But if we focus on this message passing function and the aggregation function that it implements, we see here in this sort of very general form how it's written, that we aggregate all the feature information over the one-hop neighborhood. So So if we're in a graph like this toy example here on the right-hand side, we have certain regions in the graph that are very densely connected, right? So if we take an edge in that densely connected area, then the two vertices that form that edge share a lot of common neighbors. So if you think about computing this aggregation function, basically it aggregates very similar or almost the same information in such a neighborhood. And then we feed this message in the update function, and this message basically guides how we update the representation of that particular node. So basically those nodes are seeing the same or very similar messages over and over again. And that leads to a representational collapse, right? And in such very densely connected regions, that already happens after just a few iterations, that we basically smooth or average out any distinguishing information. And unfortunately, the graph convolutions, which are one of the most widely used ways of implementing message passing, suffer from those. So let's take a closer look at that. So what you see here written on the slide is a very general way of writing graph convolutions. So this is basically you see here each term sort of corresponds to the operation in each layer. A is the adjacency, X are the features, and then W are the learnable parameters in the update function. And of course, such functions are permutation equivariant, right? So they respect fundamental symmetries of graphs. So now if we take a look at the training dynamics, if we look at how those features are getting updated layer by layer, then what you see here on the right-hand side is in a very abstracted way, the update equation that is implemented by this. Of course, here we have stripped away some of the details of the aggregation and the update function, but in principle, this is the dynamic equation that we see. And then you see here in the plot this sort of representational collapse to a unique fixed point, right? So this is an illustration of oversmoothing. And for future reference, I should say what the task here is. So this is really a toy task. We give the network a ring graph, so it has n nodes, and they're all connected and form a ring. And we mark 2 nodes in that graph, here shown in red, and ask the network to learn the distance between those 2 graphs. And that's, of course, a toy task that exhibits this feature that we need to encode long-range dependencies, right? If the 2 red nodes are very far apart in the ring graph, then we need to capture long-range dependencies well. Otherwise, we have no chance of learning that. So this is what happens in the standard graph convolutional networks as we usually implement them. So let me tell you what we change about that. We basically make a very small change to the way we implement the graph convolutions. You see that here in the equation. So again, A is the adjacency, X are the features, and then the parameters here are chosen to be a unitary matrix. And this sort of redesign of the graph convolutions we call unitary graph convolutions. And I should note that in a first order approximation, we actually recover the standard graph neural networks. But if we don't go with the first order approximation, but consider larger t, then we get a different kind of graph convolutions. I should note here that this U, since it's a unitary matrix, it has it's complex valued, so it has complex entries. This is still from an engineering perspective something that we can effectively implement. We do also have a version in the paper that uses some tools from group theory to actually find a version of this that has real valued entries. But for sort of the sake of keeping this short, I'm not going to go into details of that, but you find it in the paper. Okay, so if we go back to our toy learning task of learning the distance between the 2 red nodes, and the kind of learning dynamics that we observe from this. Here we have a cross comparison of the standard graph convolutions and of these unitary graph convolutions that we just defined. So here again, we look at a simple dynamic equation to simulate this, which is an abstracted or simplified version of the unitary graph convolutions. And you see here that the pattern that emerges is very different from the standard graph convolutions. We don't have this collapse to a unique fixed point, but we actually see a wave-like pattern. So the messages propagate in a wave-like pattern throughout the network. We don't have a unique fixed point, and this is why we don't see this over-smoothing behavior. We don't have this representational collapse. And then one can actually make this very formal. So one way to analyze or quantify the amount of over-smoothing that we expect in a graph, that depends on the geometry or the topology of the graph. And one way of measuring this is with respect to its spectrum, so the properties of the graph Laplacian. And the Rayleigh quotient is one way of characterizing the structure of the spectrum. So in terms of this measure of over-smoothing, we can show that the standard graph convolutions amplify over-smoothing as they get deeper, which is exactly what we see in practice and what's illustrated here in this toy example. But the Rayleigh quotient is invariant under unitary convolutions. So provably, as we add more layers, we don't run into this representational collapse. We don't see any over-smoothing. And even if we were to make the network 1,000 layers deep, we provably would not see this behavior. So this is just stated very informally here, but you can formally prove that. So if you're interested, please take a look at the analysis in the paper. I should note, I'm talking here about the application of graph convolutions, of unitary convolution. Like, closer? Okay, okay, thank you. Yeah, so I'm talking or focusing here on unitary convolutions for graph machine learning, so how we can integrate unitary convolutions into graph neural networks. And this is not only because this is a conference on learning on graphs, but also because those instabilities are particularly well studied in graph machine learning and also known to be particularly harmful in those settings. But as I mentioned initially, those instabilities, vanishing and exploding gradients, is something that we also see in other architectures, including in other structured or geometric models like more general group convolutional architectures. And there's a way to define these unitary convolutions much more general and allow us to build provably stable group convolutional architectures as well. So this is a nice extension that I just want to mention briefly. Now let me show you some experiments. So before looking at some benchmark data sets, let's go once more to our toy example of the ring and learning the distances between the two red nodes. And what you see here on the right-hand side is the comparison of performance of a number of different architectures, including some that were actually designed to counteract or suffer less from over-smoothing. So the dotted line here that you see, this is the trivial performance. So basically you can think of the model just randomly guessing. This is when it hits the dotted line. And then you see around this dotted line, actually most of the models that we tested here, including the standard vanilla graph convolutions that we had seen earlier, if we add residual connections, so this is the green line, residual connections are usually added specifically to overcome those instabilities. But you see on this very difficult task where long-range dependencies really matter, this also doesn't get anything better than the vanilla GCN. Spectral convolutions, for instance, were also or sometimes mentioned as suffering less from this, also only get trivial performance. Graph attention networks do a little bit better than trivial performance, but marginally. And the only two models that are able to learn the task here that get zero test error are the two variants of our unitary convolutions, the one that I showed you earlier, and then this alternative formulation with the real-valued graph convolution operator. So at least in this sort of toy task or theoretical task, we see exactly what the theory would predict. Now let's take a look at some benchmarks. And we are certainly guilty here of sort of the older benchmarks. I was very interested to see the new graph bench that we heard about in the previous talk. So we should definitely expand our analysis here to some of those newer benchmarks. But the ones that we chose in this paper was first the LRGB benchmark that was a couple of years ago designed to have tests that specifically require learning long-range dependencies. So in line with the motivation for this extension of graph convolutions. And then you see here in the first block in the table standard message passing architectures or standard message passing architectures that typically perform pretty well on those tasks. So or were at the time we wrote the paper near the top of the leaderboard. And then in the second block, those are some graph transformer style models. Again, choosing here models that perform or performed at that time near the top of the leaderboard. And then the last block are our models. And you see here that the unitary graph convolutions can clearly outperform the standard message passing models on these LRGB tasks. And we're about comparable, so competitive against the graph transformers. So we were pretty happy with seeing those results. And then the second benchmark that we tested is on our heterophilic graphs, so a benchmark that has heterophilic tasks. This choice was motivated by the fact that it's known that in heterophilic settings, oversmoothing is particularly harmful. So this is again a task or tasks chosen in a way where we exhibit where we think that our architecture could exhibit benefits. And here we have a comparison with message passing architectures only, because each of those graphs is relatively large, so it's not easy to run the graph transformers on those larger data sets, but we see here that we very comfortably outperform the best reported numbers for the passing architectures. Okay. And that brings me to the second part of my talk. So as I mentioned, we're leaving deep learning on graphs, but stay with geometry. And we want to, I first want to tell you a little bit about discrete Ricci curvature and its associated geometric flow. And then we want to use that to analyze the evolution of feature representations in feed-forward neural networks. So maybe not everybody or not many people in the audience will have a background in differential geometry, but you have probably heard about curvature in the classical sense, and probably also have some intuition on what curvature means. So as just a very sort of high-level intuition, if you look at the three toy manifolds here in the upper right corner, we have a Euclidean plane, which is flat, right? So it has curvature 0. Then if we're on a sphere, we have positive curvature. And then you might have encountered these satellite structures. That would be an example of a manifold that has negative curvature. So this sort of standard notion of curvature that's typically defined in the continuous setting is in itself not one-to-one mappable to the discrete setting. So if our data is not, or if we're not talking about a manifold, but about a discrete data structure such as a point cloud or maybe a hypergraph, a simplicial complex, and of course graphs, then we can take the standard notions of curvature and define them one-to-one in the discrete setting. And that is because those notions of curvature are typically defined in terms of the differential structure, and there's no natural differential structure in discrete spaces. But what we can do instead is to build curvature notions via curvature analogies that recover some of the properties that curvature has in the continuous setting. So not all of them. We can typically not expect that we have a one-to-one correspondence, but if we care about certain properties that curvature has in the continuous setting, we can recover them in the discrete setting. And there are various proposals for how to define notions of curvature. In this talk, I'm going to focus on discrete notions of Ricci curvature. So that's one particular notion of curvature in the continuous setting, but not the most general one. And I will only cover one notion that was introduced by Olivier a couple of years ago. So Ricci curvature, I won't go into like all of the formal details here, but basically what we had talked about here in terms of intuition for what curvature measures on toy manifolds, this was with respect to sectional curvature. And Ricci curvature you can think of as a local average of sectional curvature. And why this is interesting both in differential geometry and also if we work in the discrete setting, is because it can tell us something about volume growth. So it measures essentially the rate of geodesic dispersion, how fast do geodesics on the manifold disperse. So Olivier's notion of Ricci curvature that we want to focus on here, the kind of analogy that we want to build, or the defining property that is used to define this notion, is a relation of the behavior of random walks and Ricci curvature. So in the continuous setting, one can show that if we start two random walks at nearby points on a manifold, then if that manifold is locally negatively curved in the sense of Ricci curvature, then those random walks with high probability will draw apart, so will disperse. Right? Negative curvature indicates volume growth. And if we have locally positive curvature, then with high probability, the two random walks will stay nearby. And this is a nice property to build an analogy in the discrete setting, because random walks is something that we can study very nicely in the discrete setting, and where there's already a lot of literature and a lot of mathematics about the behavior of random walks in the discrete setting. So for our purposes here, if you look at the figure on the right-hand side, we want to define curvature at the level of each edge in the graph. So let's take the red edge here. And then we have U and B as the adjacent nodes. And then we can start random walks on each of those nodes. And let's consider, for purposes here, just uniform random walks. So each of those random walks with probability 1 over the degree will move from U to one of its neighbors. And then this notion that you see here defined by Olivier kind of mimics the behavior that we expect from the continuous setting. So we want that the curvature is negative if the two random walks disperse. So if they're likely to draw apart. And that happens if U and V don't have a lot of common neighbors, right? If the neighborhoods are overlapping a lot, then it's likely that the random walks stay close by. If there's not a lot of overlap, then it's likely that they disperse. And this overlap of the neighborhoods, this is one way of measuring this, is to say we look at the two measures that those uniform random walks started at U and started at V induce, and then measure the optimal transport distance between those two. Here, the Wasserstein-1 distance that you see in the lower left corner, if you need a reminder. So this term, or the information that we get from the Wasserstein-1 distance of those two measures tells us how much overlap essentially there is between those two neighborhoods. So it's large if there's not a lot of overlap, and it's small if there's a lot of overlap. And then the shortest path distance that you see here in the denominator, so dg between U and V is just 1 in this case. If we are in an unweighted, undirected network, and then you see if we have 1 minus a large term, something large, then we get a negative curvature value, and if we have 1 minus something small, we get a positive curvature value. And with that, we sort of recover, at least in spirit, the kind of behavior that we expect in the continuous setting. So equipped with this notion, a sort of natural question that one might ask is, so we built this notion via an analogy. Do we actually recover the true Ricci curvature in some sense? And one setting for analyzing this is using geometric graphs. So geometric graphs essentially allow us to kind of build a discrete approximation of a data manifold. So let's say we have a point cloud that was sampled from some low-dimensional manifold. We don't have access to the data manifold. We only have those points given, and we have them given in the ambient space. So let's say we have a low-dimensional manifold that lives in some d-dimensional real space. Then all we have given is this point cloud. We don't have any access to the manifold. We don't know anything about it. This point cloud we can turn into a geometric graph by associating one vertex with each point in the point cloud. And then we draw an edge between 2 of those nodes if the corresponding points are within an epsilon distance, right? And then as we vary epsilon, we get a family of geometric graphs. So that's a pretty standard construction that probably you've seen before. So if we now want to say something about to what extent that geometric graph inherits the geometric properties of the underlying manifold, and if we measure some discrete geometric quantities on that geometric graph, can we recover what's happening in the continuous setting? Then we look at so-called continuum limits, right? So if we were to sample more and more points, we get a denser and denser sample from the manifold. Then sort of in the continuum limit, we're mimicking the underlying data manifold. And there's actually been quite a bit of work in the differential geometry, discrete differential geometry literature on various different quantities. So the graph Laplacian, for instance, how that relates to the Laplace-Beltrami operator. If we measure distances on the geometric graph, do we recover the geodesic distances of the underlying manifold? So there's been quite a bit of work on that. What hasn't really been looked at is what happens for Ricci curvature. So this is what we did in this work. And there are 2 flavors of this problem that we can look at. So the first one is sort of a local consistency. So if we look at the curvature in the neighborhood of 1 point, in the neighborhood of 1 node on the geometric graph, does that recover or approximate the Ricci curvature in the neighborhood of the point that we have sampled from the manifold? And in fact, this is true. We can show such pointwise estimation results. Here's an informal statement of the kind of guarantee that we get. And you see here that we get non-asymptotic approximation guarantees. So we can precisely say with a point cloud of n points, how well can we approximate the curvature of the data manifold. And then there are some other dependencies on the dimension of the manifold, for instance, and also on this epsilon neighborhood radius, which we have to choose very carefully, right? You can imagine if we choose a very small epsilon, then we have a disconnected geometric graph, and it doesn't inherit much of the geometry of the manifold. And if we choose epsilon too large, then we have a very, very connected graph approaching a complete graph in the limit, and that would also not inherit much of the geometric information. But if we choose epsilon wisely, and in the paper we analyze how specifically to choose epsilon, then we get these non-asymptotic convergence guarantees. We can also learn global bounds on the Ricci curvature. So similarly here, we get non-asymptotic convergence results with the same sort of caveats that we had before. So we can prove, so the takeaway from this is that this Olivier's discrete Ritchie curvature that we measure on the geometric graphs does allow us to characterize the curvature of the underlying data manifold. So this is sort of the theoretical justification for the analysis that we want to do now. And then I need to introduce one more quantity, again, briefly going back to differential geometry. So in differential geometry, another tool that's closely connected to Ritchie curvature, and that's very important in various settings, is the Ritchie flow. For completeness, I've written the definition here. So it's a nonlinear PDE that tells us something about the evolution of the Riemannian metric with respect to the curvature of the manifold. And then Olivier, when he proposed his discrete notion of Ritchie curvature, also proposed a discrete version of that Ritchie flow. I should note here that those consistency results that we get in for the curvature, we don't have for the flow, unfortunately. But there's some theoretical properties of this Ritchie flow and what it does to the evolution of a geometric graph. Some of that is known, in fact, including one result in a paper that we published earlier this year, which I'll detail shortly. Okay, so for the analysis that we want to do now, we want to look at standard feed-forward neural networks. So I'm assuming everybody here is familiar with those, just written here for completeness. And of course, if those networks have a nonlinearity, such as a ReLU activation, we call them nonlinear networks. And if we don't have activation, then we call them linear networks. So this is a distinction that we will make shortly. And here, for the purposes, we will always assume ReLU activation. And then how do we, what's our model, our framework for feature geometry? So we assume that our input data is sampled from some manifold, right? We don't have access to that manifold. We don't have access to the sample distribution. We just have access to the input data. So you can think of that as the point clouds that we saw earlier. And we can build a geometric graph to represent that data. So you can kind of think of this as the sketch on the right-hand side. So let's say we have a manifold where points sort of on the left side are in one class and points on the right side are in another class. And then we would expect that if we build a geometric graph, we sort of mimic this structure in the geometric graph. And then as the networks or the layers of the network map this input data to feature representations. So we will be looking at how these transformations shape the geometric graph that represents our data. Okay. I will show some experiments as we and some theoretical results as we go along. Just want to briefly show you here what how the data sets look like. Those are all pretty small data sets, and some of them synthetic. That has to do with the computational complexity of computing some of those quantities that we use here. So if you think back to how we had defined Olivier's Ritchie curvature, for instance, that requires computing the Wasserstein-1 distance. So we have to solve a lot of optimal transport problems, which has a cubic complexity. So this analysis is not something that would scale to pretty large data sets. That's why we stuck to things like MNIST, Fashion MNIST, and CFOR here, and then also looked at some of these synthetic data sets that are sampled from low-dimensional toy manifolds. And we look only at the binary classification setting, so you already see that in the synthetic data sets. And then for the benchmark data sets, we always subsampled to classes to stay in the binary classification setting that we also analyze in the theory. Okay, so we want to use this notion of discrete Ricci curvature and the discrete Ricci flow to understand something about how those geometric graphs that represent our feature geometry, how those evolve over time. So the quantity that you see defined here on the slide basically tells us something about the average change in distances from layer to layer. And that has something to do with how the node neighborhoods in the geometric graph expand or contract. And we would expect if the evolution of the feature geometry mimics a Ricci flow, then we should be able to see this by a strong negative correlation of this average change in distances and the Ricci curvature, right? That would sort of mimic this discrete Ricci flow that we had defined earlier. So the local Ricci evolution coefficients that you will see in the subsequent analysis are essentially a Pearson correlation coefficient that we compute across layers. It's defined here. I should note that the curvature that you see here is a sort of local aggregate of the curvature at the node level, right? Remember, we had defined curvature earlier at the edge level, but for this analysis here, since we want to look at sort of the geometry or approximate the geometry in the neighborhood of a node or point on our data manifold, we need this like local aggregate. And that's also actually a quantity that's well studied in the discrete differential geometry literature, sometimes called the scalar Olivier curvature. Okay. So first analysis, so this is a subset of the results on some of our some of the data sets that you saw earlier, tracks exactly those local Ricci evolution coefficients. And we see here across the board negative correlation at almost all of the nodes in the geometric graph. So this is strong empirical indication that, in fact, the evolution of our feature geometry does mimic a Ricci flow. And then we can also say some more formal things related to this, namely why this might be the case. So if we look at, so here you see in the upper row, again, this toy manifold that we saw earlier. This is sort of a schematic representation of how the data manifold might look like in a binary classification setting, and then the corresponding geometric graph. And then in the evolution in the upper row would be how we might imagine class separability emerging as the sort of from layer to layer as the model learns feature representations. And then this would correspond to an emergence of community structure in the geometric graph. So the geometric graph would be rewired in a sense, so that whereas initially we have a lot of connections between the two communities, in the end we only have very few connections between the two communities. So in this setting, it would be difficult to recover or detect the two communities, but in a setting like this, it's very easy to label the nodes according to their community membership. And in fact, one can show for this discrete Ricci flow that in fact, if we take such an input and we run a discrete Ricci flow on that geometric graph, that we see exactly this behavior. So the emergence of those, this rewiring that lets the community structure emerge, this is something that one can formally prove that this happens under the Ricci flow. So this together with the empirical results that we see here provides maybe some intuition that the evolution of the feature geometry evolves according to a Ricci flow. some more sort of empirical evidence for this is shown here. So this emergence of community structure is also something that we can measure. There are a lot of quantities in the graph theory and network science literature on measuring the presence of community structure. Modularity and normalized cut are two of them. And we see here also with respect to those quantities that as we go sort of across the layers and analyze the structure of our geometric graphs, we have this emergence of community structure. We also did some more theoretical analysis relating to the structure of the network and which components are necessary for this behavior and for the model to learn the corresponding transformations that allow this emergence of community structure. So one thing that we know and that you can observe empirically is that if we throw out the nonlinearity, so we would use a linear neural network, that this emergence of separability, or that the model learns to perform binary classification, is often either very difficult or the model can't really learn that task. And in this this geometric framework, we can actually prove why that is the case. Again, those theorems here are just stated informally, so if you want to see the details, please take a look at the paper. But in this informal statement here, you see the feature transformation map that the model learns. And we can show that if the model does not have a nonlinearity, then it's not able to learn this sort of rewiring of the geometric graph that lets community structure emerge. If we put an activation back in, so let's say if we choose ReLU activation, then the network is provably able, the model is provably able to learn this rewiring task, and community structure can emerge in the geometric graph corresponding to the separability in the learned feature representations that's needed to successfully perform a binary classification task. Okay, and then I have two more slides on other sort of aspects that we can observe in this in this geometric framework, or through this geometric lens. So we can also track those local Ricci evolution coefficients across epochs. So look sort of during training, how the structure of our geometric graph changes, and how we can basically measure that in the local Ricci evolution coefficients. So we see here on the right-hand side that we first have this negative correlation. So that sort of indicates that the model rewires the geometric graph is being rewired. So the crucial geometric information is being learned. And then it plateaus. And this happens once the model reaches, or once the accuracy of the model saturates. So once this plateauing starts, this sort of coincides with the model having reached its peak accuracy, and it has captured all the necessary geometric information. And then if we continue to train the model, then we see the local Ricci evolution coefficients increase again, and that coincides with the model starting to overfit. So in a sense, what I've written here towards geometry-informed stopping, so beyond this sort of theoretical lens, one could imagine a setting where we might be able to track some geometric information. We can probably not compute the Ricci curvature everywhere. That would be quite expensive, but maybe a proxy of that, or there are approximations of Ricci curvature that one can compute much cheaper, and where one doesn't have to solve these optimal transport tasks. And a geometric characteristic like this could be used as sort of tracking this evolution of the feature geometry, and maybe giving rise to a principled stopping criteria. But this is sort of future work. And then one more analysis which relates to the evolution of feature geometry again across the layers, and in particular relating to how many layers we should choose, so how deep of a network we might need. And we see here that there's sort of a critical number of layers at which the model reaches peak performance. Afterwards, more layers don't help or actually degrade performance, right? So you see that here. This is just one example. We run this on many examples. But in one example, you see here sort of the typical situation where there's a critical number of layers that leads to optimal performance. And coinciding with this, we can look at the evolution of the feature geometry across the layers, and there is correspondingly, like we get more and more negative local Ricci correlation evolution coefficients up to the critical number of layers, and then afterwards it increases again, showing us that, or indicating that basically at that point the model has learned the crucial geometric information, and more layers don't help or actually sort of degrade the geometric information that we have captured in the earlier layers. So again, if we could find a good way of approximating or efficiently computing this geometric information, those local Ricci coefficients, then that could help us to design a proxy or heuristic for choosing an optimal number of layers. Okay, so this was my last technical slide. So just briefly to summarize what I talked about, and also to give you the references in case you want to learn more. So in the first part of the talk, we talked about deep learning on graphs and challenges that arise in deeper graph neural networks related to instabilities such as oversmoothing. And we talked about how to redesign graph convolutions in a way that those effects are provably avoided. And then in the second part, we talked about Olivier's Ricci curvature and its associated geometric flow, how that discrete notion of curvature relates to the classical Ricci curvature, and how we can use this framework as a lens for studying feature geometry in feed-forward neural networks. And here are the co-authors of this work. Bobak Kiani, former postdoc of mine who's now at Bowdoin College as a faculty, led the work in the first part, and then Nicolas Garcia-Trios and Moritz Hehl are the main authors on the work that I covered in the second part. Okay, and very last note, we're hiring PhD students and postdocs, so if any of you is interested or is on the market this year, please feel free to reach out. All right, thank you, and I'm happy to take questions.
Thank you, Melania. Is there any question from the person?
Thank you for your talk. And when you mention like I'm very interested in when you say like the stopping epoch criteria. So is it like when you are training the model, you track the Ricci flow and look at the separability of the geometric graph, and then you can decide like where is the best stop? And that is the question one. And question two is, I wonder how this stopping criteria is compared to like what we usually use. Like we just evaluate on the validation set, and based on the performance, we choose the stopping criteria. So like I wonder their difference in connections.
Yeah. So you would only need to track sort of compute the Ricci curvature maybe every couple of epochs, and track how that evolves, right? So this would be your first question, like what would be involved. So you have to construct these geometric graphs that approximate your the transformations of your feature geometry, and then you would have to compute the Ricci curvature of that. And that's computationally probably less efficient than sort of other techniques that are used as a stopping criterion. So this is why I said that's sort of not, I'm not claiming that we sort of solved that in the paper, but this is one direction where this could go if we could find efficient way of tracking this geometric characteristic. But yeah, due to the computational cost of that, we haven't widely evaluated that against other techniques that are currently used as a stopping criterion. So to your second question.
Hello, thank you for nice talk. And I have a question about your consistency results. So in central risk analysis, you assume data points being sampled uniformly at random with line manifold. And I think with, in real world, I mean, this of course can be biased by some hidden confounders. So I was curious if like any guarantees can relax assumption.
Yeah, so if I think, yeah, if I understand correctly, you're asking basically in this setting here, those results, if we have those for non-uniformly sampled point clouds.
Exactly.
We don't currently have. Yeah, that's a great question. I would imagine that it's possible to extend this, but it would, I think, like in order to recover those results that I mentioned here, there non-trivial additional ideas are needed. Yeah, this is really only a first result for this discrete to continuum consistency analysis of Ricci curvature. But even for other geometric characteristics, there's not a lot known in the non-uniformly sampled setting. So this is a quite difficult question, but certainly interesting. Yeah.
Thank you.
Any other question?
Yeah, thanks for the nice talk. Regarding oversmoothing, so you define GCN without nonlinearities, right?
Oh, in the first part?
Yes.
No, they have also they have nonlinearities. Yeah, this was just in the second part.
Oh, I see.
Because of those evolution yeah. So this what we're plotting here is not the models that we run. This is just an abstraction to kind of illustrate those dynamics. This hides like a lot of so this is not the dynamic equation of the actual architectures. This is just an illustration.
No, I think at the beginning when you defined the GCN layer, you said
yeah.
Yes.
Oh, yes. Here also. So in the definition, I left some of those details out to make it sort of easier to understand. You know, the changes for the unitary graph convolutions, but there are lots more sort of details that go in the actual results. Yeah.
So you have nonlinearities.
Yes.
Okay.
Yes.
Thanks
yes.
a lot.
Thanks for the great talk. I have a question regarding the unitary convolutions. There are other networks that also define different convolutions that avoid oversmoothing, for example, shift convolutional networks. Do you know how these compare to those?
Which was the one that you mentioned?
One example is shift convolutional networks, but there are many others, like just other kind of convolutions that are maybe, it's similar to your method, they are more complicated and they avoid oversmoothing. And I'm curious to know how, like what are the difference or how they compare in performance maybe?
Yeah, so we have the ones that you see here in the plot are the only ones that we have compared against. So the sheaf convolutions that you're mentioning, we haven't compared against. This selection here was driven by what has been reported to work best in the literature. So prior sort of changes in the model to avoid these instabilities were reported to be quite successful, for instance, for residual connections. That's why we included that here. But yeah, some of these, there are many other proposals that we haven't compared against, but that sort of people previously have compared against and have found that they work less well than some of the interventions that we tested. Yeah.
Okay, thank you.
Yeah, but it was not a sort of maybe not completely comprehensive. So good question to maybe extend that. Yeah.
Hi. It's very interesting to connect the geometry evolution in the deep neural network with the rich flow. So I'm just wondering whether it's also depending on the task of the deep neural networks, because as far as I know, the rich flow will at the end lead to some community structure. So because your deep neural network is doing some classification, so that's why at the end they will also have some clustering structure. That's why they can have the connection. But if you change the task, maybe that will be different.
Sure. Yeah, that's very possible. Like here, this is certainly a restrictive analysis, right? We look at very specific models. We look at a very specific task. But yeah, most of the motivation for this work was like a theoretical analysis. So we stick to pretty simple architectures that we can theoretically analyze and simple tasks that we can theoretically analyze. But yeah, absolutely agreed. That would be interesting to look at more state-of-the-art architectures and also more state-of-the-art tasks. Yeah.
Yeah, thank you. So actually, I have a follow-up question. So because there is some analogy, do you think we can use rich flow as some like a surrogate to replace the original deep network to just make it simpler?
You mean like
Yeah, so
not training the model, but just
not training the model,
doing
just,
the initial
flow. Yeah.
So I would imagine in this sort of in those simple settings, probably yes. I mean, there's a whole this paper that I referenced here, we published earlier this year, is in fact about community detection with Ritchie-Flow. So there's a whole class of algorithms that uses Ritchie curvature and Ritchie-Flow to perform community detection. So in a setting like this where the task that the model has to learn essentially amounts to community detection on the geometric graph, yes, you could probably use like a Ritchie-based algorithm, or you could use spectral clustering or something, and you would probably find the same result. But I would imagine once you go to other tasks or more complicated data sets, more state-of-the-art architectures that with a simple community detection algorithm, you won't be able to recover this structure. Yeah. This was really chosen here. So this is obviously only a schematic illustration of what's happening, and the tasks here were chosen so that it mimics the theoretical analysis that we do. Right? There's a gap here between sort of what's happening in practice and what we did here to be well aligned with the theoretical analysis.
Yeah, thank you. So actually for this paper, so did you notice there is another paper about 10 years ago? It was published by Dr. Jie Gao. So they also had a similar method using rich flow to detect the community structure. I think, yeah, I don't know what's the difference, but it seems the idea is quite similar.
Yeah. No, I'm aware of this work. Yeah. So this is on community detection, right? This hasn't. There's no connection to deep learning and neural networks. But yeah, there's one very foundational paper on Ritchie-Flow-based community detection from him. Yeah.
Okay, thank you so much. So I also have a very quick question. So have you considered using these coefficient, Ricci curvature coefficient, for studying the, let's say, the generalization, like the double descent or the, for example, grokking phenomenon, because it's happened in the geometry space?
Yeah.
So
yeah, so I very briefly hinted on this here. We have more on that in the paper, but yeah, we believe that there are connections, and you can. This is just one example plot, but yeah, you see if you look at those plots at the analysis, you see sort of the double descent phenomenon. Yeah.
Okay. Before closing the session, let's thank our greatest speaker. Yeah, we are done for, let's say, morning session, and we are continuing with the tutorial. 30 minutes. Yeah, yeah. So we are starting at 11:30 for the tutorial.